Hello, my name is Junichi Tokuda from Brigham and Women's Hospital. In this presentation, we are going to overview the technologies and clinical applications of MRI-guided robotic prostate biopsy. The speaker, Junichi Tokuda, has received research grants from Siemens Medical Solutions USA and Physical Sciences Inc. related to this presentation. Here's the goals of this presentation. First, to understand the clinical background and challenges for MRI-guided prostate biopsy. Second, to understand the design considerations and the hardware and software technologies for MRI-guided robotic systems for prostate biopsy. While this presentation is focused on robotic systems for MRI-guided prostate biopsy, many of the design considerations could be applied to other MRI-guided robotic interventions. MRI-guided prostate biopsy is one of the most actively studied applications for MRI-guided robotic interventions, and I think there are many lessons we could learn from it. Here's the outline of the presentation. I will begin with a brief clinical background of MRI-guided prostate biopsy to explain why a robotic system is needed. I will then discuss design considerations in building MRI-guided robotic biopsy systems. As examples, I will show several systems that have been demonstrated in previous human studies. Finally, I will briefly discuss challenges for MRI-guided robotic prostate biopsy and some ongoing research efforts to address them. Prostate cancer is the most common cancer among men in the US and other developed countries. The standard approach to diagnosing prostate cancer is transrectal ultrasound or TRAS guided systematic biopsy, where tissues are sampled from 6 to 12 locations regardless of cancer locations. This approach often results in poor cancer detection rates. Meanwhile, there has been a great progress in prostate MRI in the recent years. In particular, multiparametric MRI and PIRA standard reporting are becoming a crucial part of prostate cancer care. Recent studies have shown that multiparametric MRI is more sensitive than TRAS-guided biopsy in detecting clinically significant prostate cancer. Naturally, it has become common to guide biopsy based on MRI. Studies have shown that MRI-guided targeted biopsy is superior to standard TRAS-guided biopsy in finding more significant cancers and less insignificant cancers. There are two ways to guide biopsy with MRI. The first one is so-called MR-TRAS fusion biopsy, where diagnostic MRI is fused to transrectal image using fusion software. The second approach is in-bore MRI-guided biopsy, where biopsy is performed in the MRI gantry. In this way, the physician can obtain MR image anytime during the biopsy session, allowing direct comparison of the needle with the MR image features, such as the tumor. Here's the comparison of MR-TRAS fusion biopsy and in-bore MRI-guided biopsy. The biggest advantage of fusion biopsy is that the workflow is quite similar to the conventional TRAS-guided biopsy. This means that the procedure can be performed even in the doctor's office. In-bore MRI-guided biopsy can only be performed in the MRI room. Another advantage of MR-TRAS fusion biopsy is the frame rate of imaging. It is real-time, allowing interactive maneuvering of the needle. For in-bore MRI-guided biopsy, images are typically acquired after each insertion. The procedure is often performed with in-scan, out-adjust approach, where the patient is moved in and out of the bore for imaging and needle adjustment, respectively. However, in-bore MRI guidance has strong advantage in confirming the needle location, while fusion biopsy only correlates the needle with the fused MRI, which is subject to image registration error. With in-bore MRI guidance, physicians can directly correlate the needle with the tumor on MR image. There are also two approaches to placing the biopsy needle into the prostate. The most common one is the transrectal approach, where the needle is inserted through the rectum, similar to conventional truss-guided biopsy. Another one is the transperineum approach, where the needle is inserted through the perineum. The procedure is typically guided with a grid template like the one used for prostate brachytherapy. Here's the comparison of the transrectal and transperineal approaches. In terms of targeting accuracy, transrectal approach could be better in the peripheral area of the prostate, but challenging in the anterior area due to the distances from the rectum. On the other hand, targeting accuracy for the transperineal approach is relatively uniform over the entire gland. The insertion depth is typically longer with transperineal biopsy, which may cause a larger needle deviation during insertion. Transrectal MRI-guided biopsy may be easier, especially for urologists, because of the similarity to the conventional truss-guided biopsy. On the other hand, the clinical workflow and setup for transperineal biopsy can be easily extended for radiation and focal treatments. Both approaches can potentially be performed either outside or inside the bore. However, transperineal approach may be easier when the patient remains at the imaging position due to the direction of the needle. One of the concerns for transrectal biopsy is the post-procedural infection, but this is not the case for transperineal approach. Another additional benefit of transperineal approach is that it can be used for post-colectomy patients when combined with in-bore MRI guidance. While there are advantages of in-bore MRI-guided biopsy over MR truss fusion biopsy, there are also technical challenges. The first one is the patient access due to the narrow gantry of the MRI scanner. In early days, open-bore scanners are used. Those scanners allow easier access to the patient at the imaging position. However, this approach is becoming less common due to the poor imaging quality of the low-field scanners and the limited usage of such a specialized magnet configuration. Recent studies on in-bore MRI-guided biopsy are mostly performed with closed-bore scanners. They are widely available, offers great imaging quality, and can be shared with other diagnostic users. But it is generally difficult to perform needle placement while the patient is at the imaging position in the bore, and it is common to move the patient in and out of the bore for imaging and needle adjustment frequently during the procedure. Another challenge is the limited accuracy of needle placement. For example, my colleague previously reported that the needle placement error in in-bore MRI-guided transperineal biopsy using a grid template was 5.7 millimeters. One simulation study has shown that the sensitivity of cancer detection drops as the needle placement error increases. In clinical practice, physicians can recover from inaccurate needle placement by repeating the needle insertions. However, repeated insertions can lead to more tissue damages and longer procedure time. One potential solution for these issues is to use a robotic needle guide. Most robotic needle guides physically direct the needle to the target defined on the image, while the physician is inserting the needle manually. A robotic needle guide can be integrated with MRI for image-based planning and confirmation using intraoperative MRI. MRI may also be used for real-time interactive imaging. The combination of robotic needle guide with an integrated MRI can bring potential benefits including accurate needle positioning, reduced workload in the MR room or in the MRI bore. The more accurate needle placement and reduced workload can also result in a shorter procedure time. From now on, I'm going to talk about design considerations for MRI-guided robotic prostate biopsy systems. First is the system architecture. MRI-guided robotic prostate biopsy systems typically consist of 4 components. They include MRI scanner, robot, controller, and navigation workstation. The robot is the mechanical device placed in the MRI scanner to physically guide a biopsy needle to the target lesion. The controller consists of computer and electric components to drive the actuator on the robot. The computer in the controller also computes the kinematics of the robot. The navigation workstation is used to plan a needle trajectory on the image and also to confirm the needle placement. In designing the robot for MRI-guided robotic biopsy, it is important to ensure the MRI compatibility of the device. There are 4 things to consider. The first is the displacement forces and torques on the device induced by the static magnetic field. It can shift the device accidentally, causing injury to the patient and the physician. The second is the heating of the device and the surrounding tissue induced by the RF and the gradient field. The third is potential malfunction or failure of the device due to the displacement forces and the torques, or the eddy currents in the internal circuit induced by the magnetic field. Finally, the degradation of the quality of MR image, which can make it difficult to navigate the procedure. I think many of us are already familiar with this, but there is a standard that defines the 3 classes of MR safety. The first one is MR safe, meaning that the device does not have any known hazards in all MR imaging environments. This includes non-conducting, non-metallic, and non-magnetic items. The second one is MR conditional. An MR conditional device does not have known hazards in a specific MRI environment with specified conditions of use. These conditions are defined by the field strengths, spatial gradients, slew rate, RF fields, and specific absorption rate. You may have additional conditions such as how the cables are routed and connected. The third one is MR unsafe. And MR unsafe devices have known hazards in all MR environment and should never be brought into the MRI room. Because we often have multiple components with different classes of MR safety in the system, it is important to consider how those components are placed in the MRI environment. The robot must be placed inside the MRI bore because that is how the device is used. The robot can be either MR safe or MR conditional. There are other components that need to be inside the MRI room, such as physician's interface like foot pedals, switches, and a display. In some systems, the robot controller is designated as an MRI conditional device and can be placed in the MRI room, maybe outside a specific Gauss line, depending on the condition. And of course, there are MR unsafe components in the system, such as regular robot controller and a navigation workstation. Those components must be placed outside of the MRI room and properly labeled so that no one will move these devices into the MRI room. These components are often connected by electric cables to exchange signals and information. These cables can transmit EM noises from outside the environment into the MRI room, causing noise on the MR images. If that's the case, it is important to apply appropriate EM filters or shielding to those cables. Some systems use optical fibers for signal transmissions to prevent from introducing EM noises into the MRI environment. To make the device either MR safe or conditional, we have to choose the materials very carefully. Ideally, those devices are made of non-conductive, non-metallic, and non-magnetic material, such as plastic. However, there are certain areas that need some structural rigidity or precision. Certain non-magnetic metals are also used for MR-conditional robotic devices, such as titanium, brass, aluminum, and certain types of stainless steel. One thing I have to mention here is that some non-magnetic metals, especially stainless steel, can be magnetized after being machined, so it is always important to test every metallic parts before assembling them. Otherwise, you may find out that the robot is magnetic after bringing in the assembled robot into the bore. And by the time it will be too late to identify the part that is causing the issue. Every electric or mechanical components must be compatible with the MRI environment. There are several types of actuators that can work in the MRI environment, such as piezoelectric motors and pneumatic motors. Unlike regular magnetic motors, these actuators do not use magnets to generate a torque. Other mechanical components like non-magnetic bearing or a linear guide are also used to make the device compatible with the MRI environment. Encoders and switches must be made of non-magnetic components and do not release EM noises to the MRI environment. In some cases, signals from encoders and switches are transmitted to the controller via optical fibers to ensure this, but they may be wired with electric cable as long as the cables are properly shielded and filtered. Testing of the device is crucial to ensure the MRI compatibility. Magnetic safety can be tested with ASTM standard 2052-15 and 2213-17. These tests allow quantifying the force and torque on the device in the MRI environment. Another ASTM standard 2182-19 is designed to quantify the heating of the device induced by the RF and gradient field. There are also standards to test image artifact due to RF noises and B0 field distortions. NEMR MS1 2008 is used to quantify the EM noise on the MR image, whereas NEMR MS2 2008 and ASTM 2119-7 are used to quantify geometric distortion of the image due to the presence of objects with different magnetic susceptibilities. The kinematics of the robot is defined by several factors, including biopsy approach, degrees of freedom, and redundancy. In principle, the transperineum approach can be simpler because it requires only 2 degrees of freedom translation and 1 degree of freedom needle insertion, whereas the transrectal approach requires 3 to 4 degrees of freedom to position the needle guide to the entry point in the rectum, and additional 1 to 2 degrees of freedom to direct the needle into the prostate from the entry point. Some robots have redundant degrees of freedom to achieve larger range of motion or to allow alternative needle insertion path to avoid obstacles such as pelvic arch for anterior access for the transperineal biopsy. In the MRI-guided robotic prostate biopsy, we need to deal with 3 different coordinate systems. Diagnostic MRI has its own coordinate system defined by the diagnostic MRI scanner. This coordinate is used when identifying the target tumor. Intraoperative or intraop MRI is defined by the intraoperative MRI scanner. Coordinate system of intraop MRI is used to localize the target. This coordinate system does not match the one for diagnostic MRI because the patient position is different, the patient landmarking is not the same, and the anatomical configuration may have changed due to the presence of the endorectal coil or part of the robot. The robot coordinate system is defined by the base link of the robot, and it is used for the kinematics. Because the target is identified on the diagnostic MRI, localized on the intraop MRI, and then transferred to the robot for positioning, the relationships between those 3 coordinate systems must be computed before the procedure. The process to find the relationship between the two coordinate systems is called registration. For the registration of diagnostic MRI and the intraop MRI, rigid or non-rigid image registration is used. Once the diagnostic MRI is registered to the intraop MRI, the target identified on the diagnostic MRI can be mapped onto the intraop MRI. Registration of the intraop MRI and the robot often achieved by scanning MR visible fiducial markers attached to the robot. Because the coordinates of the fiducial markers are known both in the robot coordinate system and the intraop MR coordinate system, the transformation matrix to convert the coordinates of the fiducial markers between the two coordinate systems can be computed. Navigation software is in charge of image analysis for planning, registration, and confirmation of the needle placement. It is often built on a medical image processing platform such as open source 3D slicer software shown on the screen, which provides features to import MR images from the scanner and the PACS, process them, and visualize them. For planning, the software is used to identify the targets on the diagnostic or intraop MRI and localize the tumors on the intraop MRI. The software is also used to define the target points and the needle insertion path on the intraop MRI. Registration between diagnostic MRI and intraop MRI and between intraop MRI and the robot may be performed on the navigation software. As I explained in the previous slides, both registration processes involve processing of MR images, and it would make sense to incorporate such features in the same image processing platform. The navigation software can also be used to confirm the needle location with respect to the target. Several MR pulse sequences are used for intraoperative planning and guidance. 2D turbospin echo or TSE provides excellent tissue contrast, often good enough to delineate the target tumor without any other images. It also presents smaller needle artifact compared to gradient echo images, allowing accurate localization of the needle. 3D gradient echo is also used for quick confirmation of 3D needle trajectory. However, its T1 weighted contrast make it difficult to compare the needle with the target tumor. For real-time monitoring of the needle placement, 2D gradient echo or steady-state free precision sequence or SSFP can be used. However, SSFP sequence generates large audible noise in general, making it uncomfortable to work in the MRI bore. The needle placement error can be evaluated in either 3D or 2D. 3D error is defined as the distance between the needle tip and the target in the 3D space. This approach takes account of the error in the needle insertion depth, but it is often difficult to measure due to the large slice thicknesses of the image. Also, if you look at the tip of the needle, like this image, you will notice that the tip does not represent the actual location of tissue sampling. 2D error, on the other hand, is defined as the radial Euclidean distance between the needle and the target. This assumes that the actual error is ignorable given that the length of the core is long enough to cover the tumor, even if there is some error in the insertion depth. There are two kinds of errors in evaluating the accuracy of needle placement. Targeting error is the distance from the needle to the planned target. This ignores the fact that the tumor or the organ is often displaced during the procedure. If the target tumor has been displaced from the original plan, the small targeting error doesn't mean the successful tissue sampling anymore. On the other hand, biopsy error takes account of the displacement of the target. This metric represents the likelihood of successful sampling of the tissue from the target tumor. It is generally difficult to measure biopsy error in other imaging modalities. However, intraoperative MRI allows measuring the displacement of the tumor with its excellent soft tissue contrast, hence the biopsy error, which is one of the advantages of in-bore MRI-guided biopsy. There are a number of studies that have demonstrated the feasibility of MRI-guided robotic prostate biopsy in the clinical setting successfully. Zangos performed transgluteal robotic prostate biopsy under MRI guidance using a commercial 60 degrees of freedom MR-safe robot system. Yeager developed 5 degrees of freedom MR-safe pneumatically actuated robot for MR-guided transrectal biopsy and demonstrated in 10 patients. In the following years, our group has published an MR conditional transperineal needle guide device called Smart Template, driven by piezoelectric actuator and tested in 43 patients. Ball published a clinical study on their 60OF MR safe robot for transperineal biopsy called MRBot in 5 patients, whereas Bommers tested a new generation of 5 degrees of freedom MR safe robot for transrectal biopsy in 20 patients successfully. More recently, our team has published a study on a 4 degrees of freedom MR conditional manipulator and tested in 27 patients. While many studies have shown that MRI-guided robotic biopsy is clinically feasible, there are also technical challenges. In MRI-guided transperineal biopsy with robotic assistance, we found that there is a large gap in needle placement accuracy between the phantom and human tests. Our analysis on the clinical data has suggested that the targeting error was influenced by some anatomical structures such as elastic skin at the needle entry point and hard structures such as the pelvic diaphragm. These findings led to new research on angulated needle insertion that avoids structures that likely cause large needle deviation and real-time MRI feedback for adaptive insertion control. Another challenge is the lack of active insertion in the existing robot. Without it, it is still challenging for the physicians to perform needle placement in the narrow workspace in the MRI bore. It is also not possible to take full advantage of real-time MRI as feedback for correcting needle deviation adaptively. There have been a number of studies that investigated the use of additional active degrees of freedom to insert the needle into the prostate. This not only improves the ergonomics for the physician, but also potentially solves the issue of needle deviation. One study published by Van den Bosch proposed an active needle insertion mechanism, which is intended to minimize the deviation using tapping insertion. My collaborator, Wartenberg, has proposed a new robot with an active degrees of freedom to perform closed-loop cooperatively controlled robot to compensate for the deviation autonomously. In summary, we discussed the issues for MRI-guided prostate biopsy, specifically the limited patient access in the in-bore workspace and the limited needle placement accuracy must be addressed to take advantage of MRI guidance. As a solution, we overviewed the technologies for MRI-guided robotic biopsy. Specifically, we discussed design considerations including architecture, MRI compatibility, kinematics, software, and imaging. We also briefly reviewed existing systems that are tested clinically. Finally, we took a look at a few research topics related to MRI-guided robotic biopsy. These are some of the people I have been closely working with related to the topic of MRI-guided robotic prostate biopsy over the past 10 years. And thank you very much for your attention.